My name is Richard Waltman. I work with computers. Thank you very much. Okay, thank you. All right. Yes, let's talk about biometrics in spatial computing. I mean, I'm a software engineer, call myself a full stack software engineer, and some days I'm writing code. Other days it just feels like I'm beating 3 different AIs with a rusty spoon I found behind my desktop computer. That was a joke. But yeah, I thought about calling this talk Biometrics and Spatial Computing, but spatial computing is this whole thing. I'm not going to get into the definition of spatial computing today because of the nature of this conference, but what I am here to get excited about, and hopefully get you excited about, and whoever could watch this later, is let's get excited about biometrics in the context of spatial computing, and how does that unlock human interaction? You can see over here on the slide, we at OpenBCI, we won an Augie Award, I think back in 2022, and I get to have all this fun confetti. Still one of my, I'm not really a selfie person, but I like the glitter on my shoulders. It's pretty cool. Let's get into it. Why biometrics and why now? Well, spatial computing needs richer inputs. We've started with Xbox controllers. Those have gotten, Xbox controller requires 2 hands. Somebody had the sense enough to say, well, let's put them in each hand. And then they said, why do we even have controllers? Why can't we use just our real hands? And then what if, how does somebody interact with that if they've lost a hand for accessibility? But there's more to who we are than just what we are physically. We have our brain, and beyond the concept of the brain, we have the mind. And beyond the mind, we all have differing opinions about what makes us who we are. And we can begin to quantify those things. This field is not new. I'm not a major voice in the field. I'm just here to try my best every day and put all of these things together, for what we can. And biometrics offer a context-aware, emotionally intelligent, hands-free interaction with XR environments. You can do this with a 2D screen, of course. There's quite a few applications. And maybe before I go any further, I'd like to point out that most of these slides that I'm going to share could probably be their own PhD program. And each I have 3 bullet points on this slide. Each of those could be their own master's thesis. So we're just going to see how are we pulling this all together in an overview. And by all means, take a picture of the slide, look up just that point later, and dig deep if it's something that really, really interested you. And when we have this context awareness and emotionally intelligence, hands-free interaction, we can start to unlock new interaction paradigms for these immersive environments. It's not just about clicking a button. It's about me. I have a little clicker here. I click the button over here, but yet I'm looking at that, and what does that mean to the AI that's running on the device? It's really crazy stuff, and it's awesome to see the work that NVIDIA is doing. We actually were at the NVIDIA conference showing the potential of how when you start to get sensor fusion and multiple different types of sensors together, we're going to need computation to step up its game, and I feel like that it's on a good pace to handle that. Oh, and of course this picture right here, this is a brain-computer interface. He's not in space. He's in one of those airplanes where they do the zero gravity testing. Works great there too. So, and we just shared this on our LinkedIn a few weeks ago. Oh, also I want to mention that the views in this talk are my own and don't represent specific stances of OpenBCI. Cool, let's continue. What are some modalities that we have in XR? Well, we have brain waves, we have muscle activity, both of which are still electrical signals of the body. I want to mention that muscle activity is much louder, like the amplitude of it, if you could think of it like they're brain waves, and so maybe some of you have worked with audio files, and those are sound waves. Brainwaves are quite small. They're hard to detect unless you go inside the brain with a chip to get past the skull. But when you're working with brainwaves and you have a non-invasive system on the outside of the skull, it's kind of like being outside a baseball park, and you hear when somebody has a home run, and you're like, well, the game started at 2 hours ago, so maybe somebody just won. You kind of have to do that, and you're going to have to infer that, and that's going to come from advanced machine learning classification and lots of training. So we have muscle activity, it's louder. We have stress response. I'll get into how we do that. Of course, we have heart rate. I monitor my heart rate regularly with my Apple Watch, very accessible sensor at this time. And then gaze tracking. Pleased to see so many eye tracking options at the conference this year, and they keep getting smaller and smaller, which shows me maybe they're trying to integrate with the glasses form factor, which is really exciting. But one of these by itself can work for today. But where everything is headed is when we combine all of these into one system. And we're going to need lots of data, lots of trials, lots of individuals. So let's get into it. Electroencephalography, or EEG. From this, we can derive, again, this is going to just be high-level overview on some of these. Some of these could be their own PhD program. And by all means, we appreciate the work in all of these different fields. You could infer from EEG cognitive state. Is the user engaged? And right now, I'm just talking about these individually. You could get user engagement. You can get fatigue from just classifying EEG brainwaves, stuff like that. You can do attention and focus. This has been done for quite some time. There's some methods that are better than others. You can put 2 sensors right here on the frontal lobe at 10-20 positions called FP1 and FP2, and you can look at the ratio of alpha to beta waves. Those are called EEG band powers, if you're taking notes and you're interested in that. We're not going to get into that today. And then you could also infer mental workload and task difficulty. And some of the best work is, traditionally, we would do there's a field called neuromarketing, and you would say, did somebody like this? How hard did they work on this task? And you would have a questionnaire, but you get much better results, and you're better at quantifying the self whenever you combine questionnaires with actionable data, real numbers, streams of numbers. And there are challenges with all these modalities. I think I need to start getting through them. We have lots of examples we're going to get into. But there's motion artifacts. You move around, moves the little sensors on your head, and that's not actually brainwaves. Google tried to make a model to detect depression some years ago, and then they ended up open sourcing that project because we may not be able to find a generalized model for classifying, is this person stressed? You can get that classification to like 60 or 80%, but it's only going to get into the 90% accuracy when you add user-specific training on top of that and ask them to do tasks, ask them questions, and over a couple sessions. So, and also electrode placement. You can see we have our 3D printed headset. You can buy all of these options today at openbci.com for ranging from a couple $100 to $1,000 or so. Couple thousand. But this right here is 3D printed, and it already figures out where the electrodes need to go based on the accepted system, 1020, 1010, 10.5 EEG placement. And that helps you target different areas of the brain. It's not like you can just throw them on anywhere you want. There's a standard for it. Let's get into electromyography. We call that EMG. From EMG, you can put these, you see the little sticky pads there. You could even put those on your face, and you can see if you're smiling, depending on the muscle groups. With this, you're going to have to dig a little deeper, if you're a software engineer, to learn about human physiology. Whenever we were talking about placement of EMG sensors on the face, we literally were looking at different images of facial muscles and saying, what about this muscle? What about this side of this muscle or that muscle? What gives us the best placement? There's subtle motor intent and micro gestures. So right now we have hand tracking. I have to do something big like this for the hand tracker to see. But what if it was just so small, right? And I believe the Facebook and Control Labs, their wrist is moving towards these micro gestures. At the beginning of the training, they'll be quite large. But then when you just do the subtle twitches, it will begin to do that, and then, that'll probably improve user experience. You could also look at just how much are you using your muscles over time, and did those signals decrease over a 2-hour activity? And that would give you muscle fatigue and tension levels. The challenges for this, it requires stable sensor contact, has to be touching. If you lose contact, you're no longer getting the reliable signals. And it could be something, let's say you're doing hand tracking, and you do something that the system thinks is the click, but you were just trying to pick up your drink. It's a false reaction. It's not really what you want. Then we have electrodermal activity. We have a device here at the top image. It's called an Immotabit. Has a couple sensors that I'm talking about today already integrated into it. You can put it at various spots over the body. Traditionally, it's done with 2 little electrodes that are on the fingers, and it measures electrodermal activity, also called galvanic skin response. It's like micro sweat. We can use this to detect arousal, emotional reactivity, stress levels, sympathetic activations, stuff that we don't consciously think about when I'm preparing for a talk and I'm starting to get, maybe nervous or something like that. The parasympathetic nervous system, I believe that's the correct part, triggers things in the body that are below us. And then we go to, if you were to go to therapy or things like that, you could realize more of this, but it happens whether we want it to or not. And then we would use something like our prefrontal cortex to be aware of what we're doing. But if you're not aware of it, and let's say you go to a therapist and they have a GSR system, an EDA system, they could tell the patient, by the way, when we were talking about that topic, I saw your stress response. And this is just this sensor. Those types of things are possible. With EDA, there's a lag between the stimulus and the response. This one takes a little bit longer. Muscles are almost right away, within the order of less than 100 milliseconds. Some EEG patterns there's a paradigm called P300. That is about 300 milliseconds. And EDA is in the order of seconds, so it's much slower. I mean, it literally comes off the body slower because it's some response from deep in the brainstem. It moves into the body. The skin takes a little while to trigger the sweat. It takes a few seconds. And there's low spatial resolution. You could put these sensors on your fingers, your toes. You could put it on the forehead. And some of those locations produce more sweat than others, and it also could vary subject to subject. Photoplethysmography. This is the one that I was mispronouncing for a solid year. And then we were doing a demonstration that I'll show you. This is PPG. You have this in your Apple Watch. You see up on the top image. Typically, we see these at the doctor's office when they get your pulse. Put it on there real quick. Heart rate, stress, relaxation, physical exertion, fatigue. It's motion sensitive when you move around on your watch. I believe Apple probably has some rejection of some data when you're moving around so much. It probably just waits for you to be calm before it tries to get a reliable signal. Also happens in hospitals. If it detects there's too much artifact in the signal itself, it'll reject the data and not give you a number that's false. And light conditions can distort the signal if there's just tons of red or green light. But actually, one of the better light sources are infrared, especially for people with, if y'all are familiar with PPG. It's based on skin tone. It doesn't provide the best data, but from our experience, infrared seems to be a little more resilient than just red or green light. Then we have eye tracking. I'm sure many of you are familiar with this. We can do it through image-based. We can put sensors that directly contact the skin. You put one on each outside of the outer canthus right here, and that gives you the horizontal. You can put one above one. You don't need to do both eyes because our eyes kind of go the same direction. You put it over one above this eye and below this eye, and that gives you the vertical. And if you did enough work, you can make an XY plot of where exactly the eye's looking at. But still, even in our experience, give the customer both. Give them image-based and give them also the muscles themselves. This helps you with visual attention, user intent, decisions, and then the context of the interaction with how long they looked at an object. We can load up a Unity scene and we say this is a gazeable object, and you literally start running stats on every object in the scene, and that's achievable today. Well, if you close your eyes a little bit, and especially when you close your eyes with image-based, you don't have, and you can also look at pupil dilation with image-based. If you close your eyes, you're no longer getting the data, and every time they blink, it's a blip in the data. And there could be drift that happens during this, and then it's also hard to tell between saccades. That's a whole other subject, and let's just move on. So behind the scenes, how does all this happen? Well, here, let's start with all the way on the left. You have physical electrodes touching the skin of somebody, and then you're going to have something like a bioamplifier that you plug this into this device physically, and then, we start to do some software things. There's firmware on the device that has to calculate the gain to get the best signals, and then we'll send that over to the software side. We'll pre-process the signals. We'll apply filters and signal processing, which is its own domain in itself. And then we need to classify. Hopefully we've removed some motion artifact in the pre-processing. Then we want to classify, was the user attentive, were they, whatever, and then let's do some interaction. And these real-time pipelines are ready today in more, not just OpenBCI products, but other things, and you can access in Unity, Python, OSC for artists, custom APIs, you name it. This is here today. This is not the future, it's today. So, let's meet Galea. Galea is an advanced multimodal biosensing headset. It has actually all of the things that I've mentioned in the picture that I showed on the first slide. We won the award for Best Interaction Product, the Augie Award. Very pleased, also won a couple of other awards at other conferences. And it's a first device of its kind to pull all of this together at the hardware level. Before that, you used to have a different sensor, a different API for every device, and then you have to calculate the lag between the other devices. There's a framework called Lab Streaming Layer, LSL, and it spawned whole experts in just LSL to how to pull all these sensors together, and every lab would have to have that expert in order to get it done. And it's not easy, right? It's, in fact, maybe a little bit painful. Like, what if one of your sensors comes out of sync? And this is built for XR. And we've already taken this on the global stage. This is our CEO, Connor Russamano. Man in the chair is Christian Bayerlane, wonderful person. And if you can see just right, went back. If you could see just right here next to Mr. Christian's right hand is a drone. And we presented at TED, not small TED, big TED. And we modified the Galea system to fit his needs. And the software that you can see on the screen, his heads-up display, I actually worked on that part. It was a lot of long nights. My wife saying, "Are you done for today?" A lot of that. But we got it done, and Mr. Christian flew a drone, robot control with biometrics over the crowd, didn't crash, We were just so happy and through the moon. And even just sharing this with you right now, the joy just comes back to my face. This is what it's all about. Accessibility, fun, interaction, humans. What are we? What do we want to do? Connor asked him, "What do you want to do, man?" He said, I want to fly a drone. I don't have great use of my hands. He has to use a joystick with his mouth, with his tongue. And he's like, so a drone controller just isn't accessible to him. And so we did it for him. And then we shared this with the world on the global stage. You can go check that out. TED and OpenBCI should pull right up if you want to see the full talk. So use cases, we can adapt the environments based on the cognitive and emotional state. We can do hands-free interaction like Mr. Christian did. We can have emotion-reactive interfaces and controls. And I'm sure you're wondering, what's the difference between the first and the third? I got a slide for that. And then we can do something even cooler, closed-loop, immersive brain-computer interfaces. It's looking like I'm going to have to keep talking for the remainder, so if you'd like to talk, just hit me up later. I'll have a LinkedIn QR code. We've got adaptive environments. We've already made a demo for this, actually 2, where your brain waves, you can see in the little picture on the laptop, those are the different band powers of the different colors, and we made a direct correlation between the room color and the actual brain waves. And the environment changes based on the cognitive state of the user. Let's take a look. And then this is the cooler representation. And I worked on this is done in Unity, and I also composed the audio for this. So. And then that little sound right there was when they change to the more dominant band power, which roughly correlates to a new emotion. Really, if you're going to do it, it lets the user know the feedback. And I actually proposed a separate talk on just the audio for that example, but I think they just wanted me to do a broad overview. And then just for fun, they're like, can we get, CEO's like, can we play Fortnite? I'm like, yes. Do you really, is that what we're gonna do? He's like, yes. Yeah, let's do that. I'm like, okay. And then like 2 days later, I'm like, here it is. So if you have these tools on hand and you know what you're doing and computer languages aren't really a barrier, this is multiplayer Fortnite with, they squint their cheeks a little bit and then it builds the ramp. It was fun stuff. And I got to play at like they held a party in New York, and I had my headset, and then I was playing with people in New York at the office party, mobile, and we were using our facial commands to build and play together. You can do, here we have, the hands are being used, but there's an activation that happens on the screen, and you think about it, and it does the activation. Here's another example of that. This is in our introduction demo that comes, we distribute this with the Galea headset to all users just so to get their creative juices flowing. And there's going to be an EMG cube that you do slight things with your eyes or cheeks. And there's an activation arrow. I'm going to go ahead and skip this, but you can just trust me that when the arrow is full, there you go, it turns the cube. So 1 by 1 Rubik's Cube. Let's see how hard it would be with a 3 by 3, but I'm sure somebody could build that if we really wanted to. And then what if the activation got harder based on your emotional state? So emotion reactive is like, let me just go to the next slide. Adaptive. Adaptive environment is going to be the car interior and the road responding to your mood. The interior color of your car changes color based on how you feel, but then emotion reactive is like the thing that you're touching when you're stressed and you don't want the person to do something erratic with their steering wheel. It makes it harder and reduces the friction of the steering wheel. Something like that. This gets even crazier. We call this a closed loop system. You measure the EEG, you assess the signals, you decode the algorithms, you control a device, and then you give some level of feedback back to the user, either haptic feedback, and essentially, even with like haptic feedback, little muscle sensors. I tried one of the vests the other day, and then that's actually a way to write information back to the brain using our existing senses. We don't have to drill into the head and write actual electrical signals. We can use our existing senses to write back towards the brain. You can use this in training and simulation to improve the effectiveness and reduce negative learning. You can use this in therapy, generative art. There are challenges in the real world with signal quality, emotion classification, like SED's its own PhD program, and we need to do all of this in an ethical way. Looking ahead, we're going to have emotion-aware avatars with co-presence, closed loop XR systems where it just, that graph that you saw, it just goes around and around, influencing us influencing the environment, and anywhere in between. And we need to make this foundational to design. So let me, I know I'm a little bit about to be over time, but I have 3 takeaways for everybody, considering all of this stuff. And let's push for some open standards and collaboration. Let's not close off the data and all that jazz. Biometrics are XR native inputs. I even have one of our devices here in my pocket. They are expressive, it's contextual, and it's personal. We are who we are, and these numbers coming off of our body, they aren't just who we are, but they can help the computers understand just a little bit more about who we are and what we intend. Biometric integration in XR is not just the future, it's happening now. You've seen the device. I have a device on my desk at home, and these devices are out in the wild now. We've shipped last year, and we're just seeing amazing results from all of our partners. And what I want to really leave you with is that biometrics are how we embed empathy into immersive experiences. It's not just numbers, it's not just a game, but how we feel can come off of our body. We can detect this with sensors, and then we can inform these LLMs, these intelligent systems that are running code on the devices, what we intend. And we can be responsible creators and developers and idea makers that just build empathy using these biometric sensors. I want to thank you for coming today. I know that I guess the links don't show up. There's a QR code from my LinkedIn. I would love to chat more about this. I hope my excitement for the field was just conveyed and that we can use this for good. Yes, it can also be used for defense, and we are seeing those applications, but even in defense, I feel that we can use biometrics to build more empathy in the world and create more peace. Thank you.
Thank you. Thank you very much.